Okay, so here we're going to develop the formula for the area of a region whose boundary is given by a polar equation. And the first thing we're going to need is the area of a sector of a circle. So that's like a piece of a circle, including the central angle. A slice of pizza, if you will. And that formula is A equals 1 half r squared theta. And that just comes from the fact that the area of a sector will be proportional to the central angle that subtends it. So by that I mean you just need to multiply the area of the overall circle, pi r squared, by the proportion that the sector takes up. So the proportion that the sector takes up is whatever the angle that it subtends is divided by the full angle of a circle, which is 2 pi in radians. So if I multiply theta over 2 pi by pi r squared, I end up with pi's canceling out, and that gets me the 1 half r squared theta. So that is the area of a sector. We'll start with that. All right, so let fancy R be the region illustrated in this figure bounded by the polar curve r equals f of theta and the rays theta equals a and theta equals b. And b minus a is in between 0 and 2 pi. And so we're going to treat this area a lot like we did in the Cartesian plane, right? So when we first started finding areas under curves in the Cartesian plane, we divided up the curve into a fixed number of subintervals. We're going to do the same thing, except we're going to divide it up into subintervals that have angles of equal width, which we'll call delta theta, okay? And so it'll look like this. All right, so what I want to focus on is just a single subinterval. So let's focus on this one that's shaded in blue. We'll call that subinterval theta I. And so it's subtended by theta I and theta I minus 1. And remember, delta theta, we'll consider that the center of that subinterval. And then f of theta I is the radius on that subinterval. So that's this distance. All right, so if I just want to find the area of that small sector, I can use this formula. So the area of one small sector would be 1 half f of theta I squared times delta theta, right? Because the area of a sector in general, remember, is area equals 1 half r squared theta. So delta theta is the angle to get to that sector. F of theta is the radius at that sector. So the area of any individual sector is 1 half f of theta I squared delta theta. And then what I would want to do is find the areas of all these other sectors individually using that same formula, and then just add them all together. And so my approximate area is the sum from I equals 1 to n of 1 half f of theta I squared delta theta. Where remember f of theta is a polar function. And then to get the exact area, we'll just let the number of subintervals once again approach infinity. And all that does is change our Riemann sum, our sigma notation, into an integral notation. And we'll be integrating with respect to theta. So our limits of integration will be the angles that subtend the region, so that mark off the region. So I'll give you that formula. That's our final formula here. All right, I'm going to pause here. Give me a hand emoji when you're good with this page. All right. Find the area enclosed by one loop of the four-leafed rows R equals cosine 2 theta. All right, well, now that we have that formula, it's just area equals the integral from a to b of 1/2 r squared theta, or r squared, sorry, d theta. Pull out the 1/2. In this case, I'm going to integrate from negative pi over 4 to pi over 4. My r is cosine 2 theta, so I'll just have cosine 2 theta squared d theta. All right, well, notice that this is going to be symmetric about the x-axis. So one thing I can do to make my calculations a little bit easier is just find this area and multiply it by 2. And so that just changes my lower limit to angle 0. And my upper limit is still pi over 4. And then I have cosine squared 2 theta d theta. All right, well, if we are integrating cosine squared 2 theta, we do have a trig identity that we can use to simplify that. Here's our trig cheat sheet. So I'm going to use this half angle formula, which is cosine squared 2 theta. Sorry, cosine squared theta is equal to 1/2 1 plus cosine 2 theta. So I have to double the angle when I'm converting from the left-hand side to the right-hand side. So since my angle already is 2 theta, it's going to become 1/2 1 plus cosine 4 theta. All right, so this equals those two canceled each other out, but when I use that identity, I bring in a new 1/2, and that's going to be 1 plus cosine 4 theta d theta. All right, now we're ready to take the antiderivative. The antiderivative of 1 is just going to be theta, so I'll have 1/2 theta. The antiderivative of cosine 4 theta, that's going to be, what, 1/4 sine of 4 theta? From 0 to pi over 4. All right, plugging that in, I get pi over 4 plus 1/4 times sine 4 times pi over 4 is just going to be pi. And then that's going to be minus 0 plus 1/4 sine of 0. All right, well, all this is gone because sine of 0 is just 0. Sine of pi is also 0, so this is gone. So I have 1/2 times pi over 4, which is pi over 8. Arc length. Well, we already know how to find arc length in parametric form. So one thing we can do, if we have a polar curve, it's going to be in the form r equals f of theta, right? And we can rewrite it in parametric form where theta is our parameter. And I can go, okay, x equals r cosine theta, y equals r sine theta, which would then become x equals f of theta cosine theta, y equals f of theta sine theta. All right. And then I can differentiate these with respect to theta by using the product rule. So dx d theta is going to end up being, what, f prime of theta cosine theta plus f of theta times negative sine of theta. So another way of writing that is f prime is the same as dr d theta cosine theta, and then it'll be minus r sine theta. And then I can do the same thing to y. dy d theta equals, and that'll be f prime of theta sine theta plus f of theta cosine theta, which I can rewrite as dr d theta sine theta plus r cosine theta. All right, so with that in mind, so this is everything we've just done. I can simplify using this. So the fact, here, let me go back for a second. The fact is that I already have my parametric equation for arc length, right? So we defined arc length in parametric equation as the integral from a to b. If theta is our parameter, it's going to be the square root of dx d theta squared plus dy d theta squared d theta. And so that's just from our arc length formula of a parametric equation. But I'm going to get this back to terms of r. So I want to be able to integrate it as a polar function like I have here. So what I'm going to do is use our equivalence. So this is dx d theta, and this is dy d theta in terms of r and theta. And I'm going to do some algebra. So I'm going to add those two to get what should go underneath the square root in terms of r and theta. And so when I do that, I'm not going to make you guys do this by hand. You can kind of just trust me on the algebra here. But when you multiply, or when you add those together, you end up with this sort of long algebraic expression that you can simplify down using trig identities to this. So it simplifies down to dr d theta squared plus r squared. And so then my formula becomes arc length is the integral from a to b of the square root of r squared plus dr d theta squared d theta. All right, so let's do an example of how we would find arc length. We're going to go back to our old friend, the cardioid, which is just 1 plus sine theta. And so all we have to do is apply that formula to finding the arc length. All right, so I'm going to go length equals integral from a to b root r squared plus dr d theta squared d theta. All right, so the first thing I'll find is just what's dr d theta. And so that's just the derivative of our function with respect to theta. So derivative of 1 is 0, derivative of sine is cosine. Great. So I'm going to get arc length equals the integral. So to trace out the cardioid, we're going from 0 to 2 pi. Since there's no angle multiplier on sine, it's just the period of sine. So 0 to 2 pi. Square root of r squared, so r is 1 plus sine theta squared, plus dr d theta squared, so dr d theta is just cosine, it's cosine squared theta d theta. All right. 0 to 2 pi, let's multiply this out. Root, it's going to be 1 plus 2 sine theta plus sine squared theta plus cosine squared theta d theta. Remember, sine squared plus cosine squared is just 1, so I end up with 2 plus 2 sine theta d theta. All right, so this isn't like a trivial integral. This is one you could solve by hand by multiplying and dividing by 2 minus 2 sine theta under a square root, and then you would have to use like a u sub. But let's not worry about doing this one by hand. Let's just pop it in the calculator. One second. There we go. And our answer is 8. Questions about that?